Well, hello and welcome to the 37th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. We were in thick of data driven control where we actually proved this fundamental lemma of data driven control, which allows us to figure out conditions under which when we have a finite time series data, say W hat, which is given by W hat 0, W hat 1 dot 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 up to W hat t, right. When is this Hankel matrix, the Lth Hankel matrix constructed from the given finite time series data, when is it so that the column span, that the columns of this matrix give us all possible L restrictions of all possible trajectories in the behavior. And it turns out that a sufficient condition for that to happen is that the Hankel matrix of size L plus n, of order L plus n, of the input only is full row rank. If this matrix is full row rank, then this is guaranteed to happen, and in that case we can just construct the left kernel of this matrix. I can just construct the left kernel of this matrix to get the MPUM of the given data, and that MPUM also happens to be the behavior, the ground truth, the behavior that generates the data. Now, I said that to numerically it makes much more sense to calculate the left kernel by using singular value decomposition, right. So, what we have here, so we have this matrix H L W hat. What is the size of this matrix? The size of this matrix is R, L plus 1 times Q, that many rows, and T minus L number of columns, right. That is the size of this matrix. In order to find out its left kernel, what we are going to do is we are going to do an SVD of this matrix, singular value decomposition of this matrix. So, we are going to get U sigma V transpose, that is the right. And what is the rank of this? We can find out the rank from the singular value decomposition itself, that is given by the number of non-zero singular values, non-zero singular values, that is the rank. We can call that rank to be equal to R. We know that this R is supposed to be equal to the dimension of this, because the column span of this is under the persistency of excitation idea. This column span is exactly equal to this behavior, I mean is exactly equal to this vector space. So, therefore, the dimension must be equal to the dimension of the vector space, and so the rank of this matrix must be equal to that dimension. Remember, we had a name for this also, DL, but whatever that is. Now, how do you calculate the left kernel? We look at this U matrix. Remember, U is U0, U1 dot 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 up to UR, then UR plus 1 dot 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 up to UM. In this case, the size is, how many columns are there? Exactly equal to the number of rows, UL plus 1 times Q. Okay. So, that is the size of this matrix. Remember, we need to collect these vectors. So, UR plus 1 transpose, UR plus 2 transpose dot 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 UL plus 1 times Q transpose. The row span of this matrix is equal to the left kernel, as we know from singular value decomposition theory, left kernel of this matrix H L W hat. Okay. Now, what is the size of each of these guys? So, whatever this is, these guys. So, you just look at one particular row. Let us say we look at this first row, U r plus 1 transpose. This we will write as U. This we will write as R 1 0, R 1 1 dot 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 up to R 1 whatever is this size. So, each of this is so each of these, what is the size of these columns? The size of these columns are L plus 1 times Q, isn't it? Yeah, L plus 1 times Q. So, that means each of these rows have L plus 1 number of blocks, each block of size exactly equal to Q. So, we have that many Q size blocks. So, if I take all of these guys as Q size blocks, so then there will be up to R L. Yeah. And then this first row of this guy of this matrix can be identified with the polynomial R 0 1 plus R 1 1 times xi plus dot 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 up to R 1 L times psi to the power L. Yeah. So, this is a polynomial vector of size q. You collect those polynomial vectors together, we get an R xi, and we can actually stop here. Yeah. This we have already seen that the kernel of R xi is in fact equal to the behavior that we had started with. In fact, this is the MPUM of the data, and because of persistency of excitation, because of fundamental lemma, this is in fact equal to the behavior also. Now, why this roundabout way of finding out left kernel using SVD? One can directly calculate left kernel, right, because finding out left kernel is just solving equations, solving homogeneous system of linear equations, right. Finding out left kernel is like solving Ax equal to 0. Why then go for singular value decomposition, and no, why not directly calculate the left kernel? It turns out that this SVD has this built in property that is robust to noise. In what sense? I mean, it seems like a magic, right, robust to noise. How is this even possible? To understand that, we need to understand a few properties of singular value decompositions. You see, last time also I had written that if you have a matrix A of size m by n and rank of A is equal to some number r, then you know that by singular value decomposition A can actually be written as a linear combination of r number of rank 1 matrices. They are given by sigma 1, then U1 V1 transpose, that is a rank 1 matrix. What is U1? U1 is the first column of the singular value decomposition of A equal to U plus U into sigma into V transpose, and V1 transpose is the first row of V transpose. So, it is a column, it is a row that looks like an outer product, therefore, this is going to be a m cross n matrix itself, and this is a rank 1 m cross n matrix. A rank 1 m cross n matrix. Then we have sigma 2 U2 V2 transpose dot 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 plus sigma r UR VR transpose. Okay, that is A. And now there is this extremely special thing about singular value decompositions, namely if I want an a hat of the same size, yeah, m cross n, but rank of a hat is less than or equal to k, yeah, which is strictly less than the rank of R, such that when I look at A and A hat, the difference between the two, this norm is minimized. So, notice what we are doing, we have a rank R A matrix A, and we are trying to find out an A hat of rank strictly smaller than the rank of the original matrix A, and in a way we are trying to approximate A by A hat. Why is that so? Because you see, when I look at this difference and find out the norm, it is really the size of the error, the volume of the error. If you call this as the error, then when you look at the norm, it is in fact the volume or the size or the length of the error, and that is what we are trying to minimize, right. Suppose we are trying to minimize the 2 induced norm, the so called 2 induced norm. What is the 2 induced norm? Those of you who have done some linear algebra will know that this 2 induced norm is in fact given by, so given any matrix A, its 2 induced norm is by definition the maximum possible amplification, right. Look at A x, look at this 2 norm, you divide it by the 2 norm and you assume that the 2 norm is not equal to 0. That is the maximum possible amplification that you can have when A acts on a vector, right. That is the definition of 2 norm. It turns out that this is equal to the maximum eigenvalue of this matrix A transpose A. This is a positive semi definite matrix. So, the eigenvalues are greater than or equal to 0 among, so those are real non negative real numbers. So, look at those non negative real numbers, find out the maximum guy and then look at the square root, that is the 2 induced norm. Okay. So, if I look at this 2 induced norm, then this is a non convex optimization problem, that is you have A hat, yeah, 2 induced norm, you are looking at the minimizer among all A hat, which satisfies the property that rank of A hat is less than or equal to k, which is strictly less than R. How do you get this A hat? Why this is a non convex problem? Because if you look at the set of all matrices, I mean if you look at the constraint set here, the set of matrices whose rank is strictly smaller than the rank of the original matrix, that is a non convex set, some non-linear very complicated looking set over which you are trying to minimize this function, not an easy task. But it turns out that singular value decomposition gives us an easy answer to that. What do you do? Remember what is A? A by singular value decomposition is sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose plus dot 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 plus sigma r u r v r transpose. The minimizer can be taken to be sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose plus dot dot dot. Where do you stop? You stop precisely at sigma k uk vk transpose, because k is strictly smaller than r, you have lesser number of such elements. In fact, A hat has a singular value decomposition using these matrices only u1 u2 u3 and so on up to uk, v1 transpose v2 transpose to vk transpose. So, therefore, A has a singular value, A hat has a singular value decomposition given by u sigma hat v transpose exactly like before. So, the size remains the same. And what is the sigma hat? The sigma hat is given by sigma 1 dot 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 up to sigma k. You stop before, you do not go all the way up to r, but you stop little before. Yeah, this is what it is. So, then obviously, it follows that rank of A hat is exactly equal to k. So, it satisfies the constraint, and it turns out that if you look at A minus A hat, then this has a singular value decomposition u sigma v transpose minus u sigma hat v transpose. So, that is obviously equal to u sigma minus sigma hat v transpose, and sigma minus sigma hat looks like the following. First k entries will be 0, then we will have sigma k plus 1 up to sigma r in a descending order, and the remaining portions will all be filled with zeros v transpose. So, this is a singular value decomposition of this guy, and you know, in the singular value decomposition, when I find out this is also equal to the largest singular value of this matrix A. So, in this case, this difference has, what is the largest singular value? This guy. This is equal to, so therefore A minus A hat, the error, its 2 induced norm is given by sigma k plus 1. That is the minimum that you can achieve by doing this lower rank approximations. Why is that so? We can quickly have a proof of this. You see, if you look at any matrix B whose rank is less than or equal to k, take any matrix B whose rank is less than or equal to k. Okay? And then we look at, so if the rank is less than or equal to B, rank of B is less than or equal to k, then what can you say about the null space of B? What is the dimension of the null space of B? See, dimension of null space of B is exactly equal to, it is an m cross n matrix, right. So, n number of columns minus rank of B. So, therefore, this will be bigger than or equal to n minus k. Okay. Now, we look at V 1 transpose, sorry, we look at V, not V 1 transpose, but rather V. We look at, so remember the singular value decomposition of A. Singular value decomposition of A has A equals u sigma V transpose. Remember, V is given by V 1, V 2 dot 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 up to V n. These are right singular vectors of A. Among these right singular vectors, we look at V 1 dot 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 up to V k plus 1, and I look at the span of these vectors. What is the dimension of this span? Let me call this guy, give this a name. I call this guy as S. Okay. What is the dimension of S? Dimension of S is exactly equal to k plus 1, right. Dimension of S is exactly equal to k plus 1. Okay. Now, the dimension of null space of B is n minus k. So, therefore, the claim is that S intersection kernel of B cannot be equal to 0, because if the intersection would be 0, then S plus kernel B, this will be a direct sum, and so the dimension of this guy will be equal to k plus 1 plus dimension of kernel of B, but this is bigger than or equal to k plus 1 plus what is the inequality? Dimension of kernel of B is bigger than or equal to n minus k, right. This is n minus k, is not it? Yeah, because B is a rank deficient matrix, its rank is less than or equal to k. So, therefore, dimension of kernel of B is bigger than or equal to n minus k. So, therefore, because if this is so, if we have this, then this is what we have, k will cancel out and we will have n plus 1, and that is an absurd statement. Why? Because this is a subspace, S is a subspace of R n, kernel of B is a subspace of R n, both are subspaces of R n. So, of course, S plus kernel of B, that is also a subspace of R n. So, therefore, this dimension is always less than or equal to n. It is a subspace of R n. R n has dimension n. So, therefore, this dimension can never exceed n, but here we are saying that this is bigger than or equal to n plus 1. So, what we had assumed here, that this intersection is 0, that must be untrue. So, therefore, this implies S intersection kernel of B is non-zero. If it is non-zero, that implies there exists a vector v hat, which is both in S as well as in this kernel. Because v hat is in S, this implies v hat can actually be written as some alpha 0 times, well, I should not use 0. It's alpha 1 times v 1 plus alpha 2 times v 2 plus dot 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 up to alpha k plus 1 times v k plus 1, isn't it? Yeah, that is how, yes, that is this description of S. Okay. Now, if I do A minus B, if I make A minus B act on v hat, what do we get? We get this to be equal to A v hat minus B v hat, but v hat is in the kernel of B. So, this is equal to 0 because v hat belongs to kernel of B as well. So, we are left with A v hat. Now, what is A v hat? What is A v 1? A v 1, remember, is equal to sigma 1 u 1 v 1 transpose dot 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 up to sigma sigma r u r v r transpose multiplying v 1, that is equal to sigma 1 u 1 v 1 transpose v 1. Everything else will be 0 because v 1 is orthogonal to every other vector v whose index is not 1. So, v 2 transpose v 1 is equal to 0, v 3 transpose v 1 is equal to 0. So, every one of them will be equal to 0. Yeah, let me not write it that way. Right. So, this is what we have, but v 1 transpose v 1 is equal to 1 because v is an orthogonal matrix, sigma 1 u 1, right. So, this is happening because v I transpose v j is equal to delta I j. Likewise, A times v 2 will be sigma 2 v 2, sigma 2 u 2, I am sorry, sigma 2 u 2, and so on up to A v k plus 1 will be equal to sigma k plus 1 v k plus 1, which then means that A v hat will actually be equal to alpha 1 sigma 1 u 1 plus alpha 2 sigma 2 u 2 plus dot 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 plus alpha k plus 1 sigma k plus 1 u k plus 1, right. So, now what is the norm of A v hat? What is this norm? You see, to start with, yeah. Right. So, what is the norm of this guy? It has a linear combination given by this, you know, it is a linear combination given by these vectors, yeah, and each of these vectors are orthonormal vectors. That means, they are orthogonal to each other and they are of unit length, all of them. So, think about it, if you have an orthonormal basis and you write some vector in that orthonormal basis, what is the 2 norm? What is the Euclidean norm of that vector? It is in fact exactly equal to alpha 1 squared sigma 1 squared plus alpha 2 squared sigma 2 squared plus dot 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 plus alpha k plus 1 squared sigma k plus 1 squared. This square is this, right, because once again uy transpose uj is equal to delta ij. Think about this. If you have an orthonormal basis, then if you write a vector in terms of those bases, look at those components, the length of those components, their Euclidean distance, their Euclidean norm is equal to the Euclidean norm of the linear combination. Now, great. So, if we have something like this and we know that there is this order sigma 1 is bigger than or equal to sigma 2 is bigger than or equal to sigma 3 is bigger dot 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 like that. Because of that, if I replace each of these guys by the smallest possible sigma value here, I will have an inequality that says that a v hat, the 2 norm whole squared, must be bigger than or equal to alpha 1 squared sigma k plus 1 squared plus dot 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 up to alpha k plus 1 squared sigma k plus 1 squared. So, I will just take out common. So, I will be left with alpha 1 squared dot 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 up to alpha k plus 1 squared sigma k plus 1 squared taken out common, or in other words a minus b sorry my bad. I will have a minus b v hat 2 norm is bigger than or equal to alpha 1 squared dot 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 up to alpha k plus 1 squared square root multiplying sigma k plus 1 divided by this 2 norm. What is this 2 norm? Once again v hat is the linear combination alpha 1 v 1 dot 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 up to alpha k plus 1 v k plus 1. These are orthonormal vectors. So, therefore, v 2 norm is equal to alpha 1 squared dot 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 up to alpha k plus 1 squared square root. This is the number. So, therefore, when you divide by v, the 2 norm of v hat, this cancels out. So, therefore, we have this, that a minus b v hat 2 norm over the 2 norm of v 2, this is bigger than or equal to sigma k plus 1. When you look at the maximum amplification of this guy over all v 2 v hat 2 such that this is not equal to 0, that max will still be bigger than or equal to this one, because each of these guys themselves are bigger than or equal to sigma k plus 1, which then means that a minus b, the 2 induced norm, will always be bigger than or equal to sigma k plus 1. So, that is a lower bound. Yeah. So, if you look at the errors, so when you have this low rank matrices which are approximates of your given matrix A, if the rank is constrained to be less than or equal to k, yeah, then the error is low bounded by this number. The error can never be smaller than this number, it has to be bigger than or equal to this number, right. And this is a tight lower bound, because I know that there is at least one guy which achieves this, namely this guy, this a hat. This has rank equal to k. So, the rank condition is met, and it has error length given by exactly equal to the lower bound. Yeah. So, if I can achieve the lowest possible number, I mean if I can achieve a lower bound, that means that is the minimizer. So, therefore, the low rank approximate, one low rank approximate a hat is in fact given by sigma 1 u 1 v 1 transpose. You start like before, but you do not go all the way up to sigma r, all the way up to the rank of the matrix. You stop well before, you stop at the kth value, that is the approximate. Okay. Now, why did I broach this topic? So, remember what were we after? We were after finding out the left kernel of this data Hankel matrix. But if the data is corrupted by noise, then the rank of this guy. So, the rank of this guy, which was under persistency of excitation expected to be expected to be L plus 1 times m plus n, it will turn out to be bigger than this number, right, because there is noise there. We do not expect the number to be like this. So, when I do this singular value decomposition of this guy, so if I find out a left kernel of this guy, because the rank is more, I will get lesser vectors in the left kernel, and so I will have a smaller, I will have a smaller equation module, I have a smaller equations, I have a smaller orthogonal complement, smaller number of equations. So, I will have a bigger behavior. So, in fact, I will end up identifying a behavior which is actually bigger than the original behavior, right. So, in that scenario, what do? We just look at the SVD of this corrupted HL, whose rank might be bigger than what was expected, but somehow if I have an estimate of this number, which is the expected rank, what I will do is I will still obtain, I will just look at this HL hat W hat, which is in fact the low rank approximation, that is u sigma up to this expected rank of this guy dl v transpose, that will be sigma hat, that will be my my approximant, although I do not spell it out whether this is indeed whether spell it out as an approximant, because I do not know yet whether this will also have the structure of a Hankel matrix or not, but I do not go into the confusion that might arise from there. Instead, what I do is I just say that look at this guy and look at the left kernel of this. That means still look at this u r plus 1, u r plus 2 and so on, where this r you take to be equal to the expected rank, that is L plus 1 times m plus n. You look at that as the rank, this as the rank, and you still look at these vectors. So, these vectors will no longer be the left kernel of the data matrix that you have, because the rank will be more, and if at all this remaining the last few columns will be the left kernel, but we do not worry about that. We just look at the way we were looking at the left kernel like before. What we will have here instead, if you look at these guys as the left kernel, that is an approximate left kernel, that is an approximate left kernel. Why is it an approximate left kernel? Because it is a left kernel of this low rank approximation of the Hankel matrix. This is the low rank approximation from singular value decomposition theory. So, that is why if I do SVD and I use this number to be the rank, the expected rank, and find out left kernel from there, so it does not matter even when the data is noisy, still I will get an approximate left kernel, and from there I can get the MPUM, the approximate MPUM. Okay, I think we have run out of time, so we stop the lecture here, and from the next lecture onwards we will look at this idea of designing, of real data driven control, of designing a controller from the data, how you can talk about stabilization through closed loop stability through this state feedback using just data. This and many more is what we are going to see in the next few lectures that are remaining. Till then, take care of yourselves. Bye.